So we're on, I guess it's part 7 of Dissymmetry of lift. And before we get away from Dissymmetry of lift, actually we never really get away from Dissymmetry of lift. When we go over the other subjects, we're going to be frequently referencing Dissymmetry of lift. But before we move on to our next subject, I'd like to talk about some things that are really important. All right, so pay attention. And also, I'm going to postulate some questions here, and let's see if you guys can answer it on your own without me giving you the answer right off the bat. I'll give you a few seconds after I ask you the question, see if you can come up with the answer. All right, so the first one is, and you guys remember, in the spirit of Ross Perot, I designed my own chart here having to do with the amount of teetering that increases as you increase airspeed. So I'm sure you guys remember all of that. All right, let me ask you a quick question. And again, this was designed, and we use 130 here as our top speed here. And this was designed for down here in good old thick air at sea level, okay? So let me ask, the first question is, if we go up in altitude, what happens to this curve right here? And I'll give you a little hint. The shape of the curve does not appreciably change. The shape of it stays the same. But what happens to the curve? Does it seemingly move one way or the other as you increase in altitude? What happens? All right, well, to answer the question, as you increase in altitude, then you have to increase the amount of collective to make enough lift. When you increase collective, what happens to teetering? Teetering increases, right? And the speed at which you're retreating blade stall goes down and down and down. So this whole curve shifts back this direction. All right, so if we're up here at 10,000 feet and we may meet our maximum amount of teetering, maybe way back here about 90 or so. Right, so as we increase in altitude, then this entire curve shifts back this direction. All right, how about, all right, so that's one thing that causes a shift, and now you know why your V&E is decreasing as you go higher and higher and higher, because this entire curve is shifting to the left, and the speed at which you would reach maximum teetering would be continuing to become slower and slower and slower as you go up in altitude. Right? Okay, that's one. How about your weight? How about the weight of the helicopter? If the weight of the helicopter is excessively high, well, let's put it this way, if your weight's increased, everything else being the same, and it doesn't matter whether you're down here in thick air or up in thin air at 10,000 feet, but if the weight of the helicopter is increased, what happens to this curve? That's correct. It moves this direction, right? The heavier the helicopter is, the more lift you have to produce. The more lift that has to be produced requires more teetering, and as it teeters, you get closer and closer to the teetering limit. Right? So when the weight of the helicopter increases, the amount of teetering increases, and guess what? V&E decreases as well. All right. In fact, if you look in the R44 handbook, look under Chapter 2 in limitations, it's going to have your chart there to figure up what your V&E is based on altitude and temperature, which is density altitude. Right? So if you look for any particular location on that chart, it can tell you basically what the calculated V&E is for that temperature range and altitude. But if you look down at the bottom of that little chart, there's a little notation that says when your takeoff gross weight is more than 2,200 pounds, the max gross weight on an R44 Raven 1, I'll use a Raven 1 for the example, the max gross weight on a Raven 1 is 2,400 pounds. Well, at speeds above 2,200, at weights above 2,200 pounds, they want you to reduce your V&E by 10 knots. All right, so now you know why. Why does that occur? Well, the heavier the helicopter is, the more lift you have to produce. When you're producing more lift, you're producing more teetering and getting closer and closer to the teetering limits on the aircraft. So if you were super lightweight, would your V&E be actually, at least your calculated V&E, be slightly faster than it would be if you were heavy? Heck yeah. The lighter the aircraft, actually you can get some small movements in V&E. But okay, how about turbulence? All right, how about turbulence? So what is turbulence? Turbulence basically is updrafts and downdrafts, and you happen to be flying through those updrafts and downdrafts, all right? If you fly through an updraft, what do you think happens? Well, number one, the aircraft goes up, that's for sure. Well, if we look at aerodynamically on the rotor disc, what is happening? Well, you have this large column of air that's coming up towards the rotor disc, and that increases the angle of attack actually on both sides of the rotor disc. So it increases the angle of attack on the rotor disc. We're increasing it on both sides, but the greatest amount of lift increase is always at the 3 o'clock position, so the blades have to teeter increasingly. And as the blades teeter, you get closer and closer to the teetering limit that the aircraft is designed for, okay? What happens in a downdraft? Well, downdraft, just the opposite happens. The amount of, you go down, because it's a downdraft, and the amount of angle of attack is actually reduced, teetering is actually reduced, and that's not as big of a concern, all right? So what, if you notice in most of the helicopter handbooks, most of the POHs for the helicopter, whether it's a Robinson or whatever, they're going to have recommendations in there that talk about turbulence, and most of them tell you to slow down in turbulence. That's a very good piece of advice, all right? And if you notice that and they all have little different formulas for like to slow down so much, but it's quite simple. If I had to ask you a question, if you wanted to slow down in turbulence, what would be about the best speed to go if you were flying through a lot of turbulence? Well, there's a little speed called the minimum descent speed, and it goes by some other names as well. But essentially what that is the speed that the aircraft, if the aircraft's flying at, takes the least amount of power to produce a required amount of lift to keep the aircraft in the air, all right? Knowing that if you're at or near that speed, how much teetering are you going to be experiencing? Not a hell of a lot, right? It's going to be pretty decent, all right? So if you're flying at speeds approaching or speeds near the minimum descent speed, the amount of teetering is minimal. That gets you farther away from the limits of teetering, and is actually much safer to do. All right? So if you get in turbulence, slow down. You've got to slow the aircraft down. And you'll also notice that here recently they've got some little stickers that we put on all the R44s that says you're only allowed to go above 110 knots in smooth air. Now you know why, all right? You can't be tootling along at 125 knots in an R44 in turbulence, because for all of the reasons that we've already talked about.